So yesterday we learned about the mean of a random discrete variable, and today we're going to learn about variance. So how do you calculate the variance and standard deviation of a discrete random variable? Are these formulas on the formula sheet? And the answer is yes, the variance is on the formula sheet. And then the standard deviation is just the square root of that. So that's how you're going to find the standard deviation. So we're going to say VAR for variance of x is going to be given by the symbol sigma, and it's of x, so that's saying it's the standard deviation of the random discrete variable x. It's squared, so that makes it variance, and it is found by the summation of each individual x minus the mean for the variable squared times the probability for that outcome. So I'm going to do an example so you'll understand that better. Or the other way you can think of this is it's the summation of the observation, each observation, minus the mean squared times the probability of the observation, or the outcome, however you want to think about that. So the symbol is this, standard deviation of x, it's sigma sub x, is the standard deviation of a discrete random variable. So how do you interpret the standard deviation of a discrete random variable? It is simply the average distance the outcomes are from the mean. So it's very similar to what we've done in the past. So we have a little example here where this is back to the roulette example. And we know that the red, black, and the corner bets had the same exact expected value. And that was -5 cents. So we're going to look at the standard deviations and see how they compare. So I'm going to show you how to compute those. So red and black, and then I'm going to quickly do this because we've kind of already looked at this in another note sheet. So the distribution, or the probability distribution, says that I can have $1 that's lost, or I can have $1 that is won. And the probability for these, 20 out of 38, and then I have 18 out of 38. And then we remember that the expected value, written like that, also mu sub x is another way to write that, is equal to -1 times its probability, 20 over 38, plus $1 times its probability, 18 over 38. So it's really just sort of like a weighted average, and that is going to be -0.05. So the probability for each of these outcomes is just weighting the values. So it's more likely that you lose, but not by much. So the odds are slightly in the favor of the casino when you're playing roulette and you're betting on the red-black. Okay, so what I'm going to do now is the standard deviation. So standard deviation of the random variable x is going to be, and I'm going to take the square root of it, and it's going to be -1 minus the mean, which is a -0.05, so it ends up being plus 0.05 squared, times its probability. So I have to, again, weight it. Plus, and now I need to do the difference between 1 and the mean, minus 0.05. So 1 minus a -0.05 is 1 plus 0.05 squared, and again times its probability, which is 18 out of 38. And this gives you approximately almost $1, 0.999. Okay, so what I want to do now is show you the corner bets, and it has a different distribution, so let's kind of do that. So the corner bets are going to look like, are going to have a distribution where you lose $1 And that happens 34 out of 38 times. And the other outcome is you win $8 because remember you win your dollar back plus you gain 8 more, and that happens 4 out of 38 times. And then I'm just going to remind you the expected value that we found was negative 0.05. So setting up the standard deviation, it is going to be -1 minus a negative 0.05 all squared, and then multiply by its probability, so I'm weighting it, 34 out of 38, plus, and then I need the standard deviation, the difference between 8 minus negative 0.05 times its probability, which is 4 out of 38. And then that is going to simplify down to approximately $2.762. So that basically is saying that even though the expected earnings every time you play are the same, the variability is a lot more for the corner bets. So that's the takeaway from that. Almost $3 is the variability or the standard deviation. So on average, the wins are going to be roughly $3 above or below your expected earnings. All right, so let's move down to the bottom part. Okay, so the question here is, can you use your calculator? So let me go, I kind of skipped that part. So yes, you can. So let me show you. So I have list 1 is where you're going to put all possible outcomes or all possible x values. Okay, so that is going to be just your outcomes. And then in list 2, you're going to put all corresponding probabilities. So you want them to match up based on the outcome. And then you're going to do one variable statistics, and you will do list 1 comma list 2, and this is really just your frequency. I've told you before you can use frequency. You don't use it very often, but so freq is what that looks like. Okay, so I want to show you the symbols you're looking for. The expected value of x is the same thing, of course, as mu of x, which is just your x bar. And when I say x bar, this is the symbol the calculator gives you. And then the standard deviation of x is simply going to be the standard deviation of x. So there's nothing to really do there. This is the calculator symbol. Okay, so I want you to open your calculator up, or get your calculator out. I'll open mine up here, and I'm going to do one of these with you. In fact, I'm going to do the same thing that we just did there. Okay, so list 1, I want to put the possible outcomes, -1 and 8. I'm going to do the corners example. Let's just do that one. So go ahead and enter in list 1, -1 is one outcome and 8 is another outcome. And then the probabilities, of course, would be 34 out of 38, just like we did earlier. So let me get in here. So list 1, and remember you can clear out what's in the list by doing clear, enter. Okay, so list 1, I want -$1 and then I want $8. Those are my two possible outcomes. List 2, it's 34 divided by 38, and that's the probability of losing $1. And then I'm going to do 4 out of 38, and that's the probability of winning $8, getting your dollar back and then winning $8. So then I'm going to do stat, calc, enter for one variable stats, and I need to make sure my frequency list says list 2. That is where I'm weighting it, essentially. I'm going to calculate it. Just want to show you where everything is. So this is my expected value, or my basically the mean of that random discrete variable. And then here is the standard deviation, 2.762. So that's what you're looking for when you do the one variable stats. We don't do much else with anything else here. Okay, so let's go back to the notes and pick up where we left off. Are there any dangers to be aware of when using the calculator to find the mean and standard deviation of the discrete random variable? Yes, there are some dangers. You must show your work to get credit, and you can show just the first few terms. You can show the first few terms, and I'll demonstrate in a minute what that looks like. And then use something called an ellipses. It's just the dot, dot, dot to imply you're following that same pattern and that same pattern continues. So be sure to turn the frequency back to 1 after using the calculator. So just make sure when you go back in and you run the next thing, so say it's stat calc and I'm doing something else, I need to make sure to turn this back to a 1 so I can graph again. And of course that won't work here because I was trying to do one variable stats here. But okay, so just want to show you that. So that is pretty much it for discrete random variables that we're going to talk about now. We're going to move into talking about continuous random variables and making sure you understand those. So what is a continuous random variable? A continuous random variable, I'm kind of running out of room here, takes all values in an interval of numbers. So I want to show you some examples of continuous versus discrete. And I'm going to try to give you information that's similar in nature, but you'll see the difference. So continuous might be foot length versus discrete would be shoe size. So it's getting at the same information but in a different format essentially. So continuous might be race time, how long it takes you to run a race, versus say the hurdles jumped. And then the final one might be age, which is continuous. It can be down to the minute, second, however you want to compute that. And discrete might be something more like number of birthdays you've had. So the main takeaway is to know that continuous is something more measurable. So put measured here. And then discrete is something more countable. So that's going to help you understand that. So, is it possible to have a shoe size equal to 8? Is it possible to have a foot length equal to 8 inches? So let's talk about that, because there are some limitations to, not limitations, but things you have to know about continuous data. Okay, so the answer here is yes, you can have a shoe size 8, obviously. Is it possible to have a foot length exactly size 8? And the answer here is no, and this is really important for you to understand something we're going to talk about in just a minute. The probability to have a foot length that's exactly 8 inches is 0, but let me tell you why. That is one outcome out of infinitely many outcomes, and 1 over some really huge number is going to simplify down to approximately 0. And that's a simple way to put this concept, but that's what we're dealing with there. So you're not going to really look at, for continuous data, when a value is exactly 8 or exactly 9, like you would for discrete. So that's one of the big distinctions. So how many possible foot lengths are there, and how can we graph the distribution of foot length? So they are infinite. That's what I was just talking about. Possible foot lengths, and you would graph using a histogram with an infinite number of very skinny rectangles that add to 1. And it ends up basically looking like a density curve. And I want to review density curves with you just real quick. It might be something that looks symmetrical of some nature. It might be bimodal. It may be something that is more uniform in nature. It may be something more right skewed, something more left skewed. But all those curves would be something appropriate for continuous data. Okay. So this next part, how do we find the probabilities for continuous variables? We will use the area under the curve, and here's why. Because the area under the curve equals 1, no matter what the shape is, the area equals 1, back from our density unit, and the probability of all possible outcomes also sums to 1. So in other words, area is the same as probability. And we will use those interchangeably. Okay, for a continuous random variable, x, how is the probability of x being less than a related to the probability of x being less than or equal to a? Since there is no distinction, or you cannot have the probability of exactly a, they are the exact same thing. So they are the same. The boundary lines add no area or probability, because remember we said the probability for x to equal a would be 0, because it'd be 1 over an infinite number of outcomes. So the boundary lines add no area or probability because it represents 1 out of infinite outcomes. Now the next part is sort of a review, but I just want to make sure you remember how to do this. So we have a scenario here. We have 3-year-old females. They follow a normal distribution. That's important. We need to know that. With a mean of 30.7 and a standard deviation of 3.6 pounds. And if you randomly choose one 3-year-old female, find the probability that she weighs at least 30 pounds. I'm going to write this as greater than or equal to, because that's what it says here, at least. But I'm going to do it the same way as I would if it just said greater than 30. So that will be equal to the probability that a z, remember we convert our x value, our raw data value, to a z score, and we do it by saying x minus the mean divided by the standard deviation, and that's going to simplify down to negative 0.19. So I'm going to draw a little curve here. Negative 0.19 will be a little bit to the left, and I'll know this shaded region there. So using table A, or normal CDF, and I'll remind you in a minute what you have to show with normal CDF, the probability for z to be less than or equal to negative 0.19 is equal to 0.4247. So that means the probability for z to be greater than or equal to negative 0.19 is going to be 1 minus 0.4247. Because remember, the table gives you the area to the left. So let me make a little note here. This is because if we use the table, we have to find the area to the left, and that is going to give us 0.5753. Okay, so let's do another one. Find the probability that a randomly selected 3-year-old female weighs between 25 and 35 pounds. Okay, I'm going to scroll down for that. Okay, so we are looking for the shaded region. I'll draw that for you. So we are looking for the shaded region, and I'll draw it like this. Roughly, looking for this region there. Or we're looking for the probability that any randomly selected female will be between 25 and 35 pounds. So with a mean of 30.7 pounds, and it's hard to read right there, pounds, and S, or standard deviation, equal to 3.6 pounds. And I want to tell you, this is important because you're basically giving your variables you're about to use. In fact, you want to, this is important right here. You got to say what the mean is, and you got to say what the standard deviation is, because you're about to use those in the normal CDF. So using normal CDF, and I'm going to say 25, 35 with my mean of 30.7, and I can do this showing the syntax because I've identified it previously, and 3.6 will equal to the probability, of course, and I'm kind of being redundant right here, but just to show you, the probability is actually going to be 0.827. So that is your answer. So we are looking for the shaded region here, or the probability that any randomly selected 3-year-old girl if I could write this out, selected, and it has to be someone from our population, obviously, with a mean of 30.7 pounds and a standard deviation of 3.6 pounds. So using normal CDF, we get a probability of 0.827. So the next question is, if P, the probability of X is less than K, is 0.8, find the value of K. So this is like working backwards, and it's saying that I want you to find K if this area here to the left is 0.8. So isn't it really asking us to find the value of female weights at the 80th percentile? So we are finding the value of female weights, well, I should say 3-year-old female weights at the 80th percentile. Okay, so using table A or inverse norm, I'm going to show you with table A. So using table A, the value of Z is equal to 0.84. So essentially we're getting a Z here using the table 0.84. That's a Z that goes with that. Therefore, our Z of 0.84 is equal to our X, which we're looking for, minus our mean, which is 30.7 divided by our standard deviation of 3.6. So K is equal to 33.72 pounds. So this is our answer. So we are finding the value of 3-year-old female weights at the 80th percentile. So using table A, the value of Z is 0.84. Therefore, if we use the formula for our Z score, we get K at 33.72. Or the other way would be to do inverse norm. And you would need to identify the mean and the standard deviation. The area to the left would be 0.80, and you would use your mean of 30.7 and your standard deviation of 3.6. And that would give you the same thing. Okay, your check your understanding, which I'm going to look at on Monday, is going to be using the same information up above, find the probability that a female weighs less than 23 pounds. So I just want you to practice that. It's pretty straightforward. Just take you a minute or two, and we will touch base with this on Monday.